Hello, ladies and gentlemen. Welcome back. We are on Chapter 9. Chapter 9.1 is dealing with sample distributions. We are going to be doing a lot with sampling and understanding why sampling is so important and how to carry out sampling. All right, we kind of talked about it in Chapter 5 when we did experimental design, but we're going to get into a little bit more detail here. If you recall from example 7.8, obviously from Chapter 7, we saw that the height of young women varies according to this. Okay, do you remember what that distribution is telling us? Okay, it's telling us it's a normal distribution with a mean of 64.5 and a standard deviation of 2.5. Okay, so you need to remember what that is telling us. Now, in that example, as the number of observations drawn increases, the mean x of observed values eventually approaches the mean, right, of the population as closely as you specified and then stays that close. So if you remember, you randomly select a few women and it jumps all over the place. You'll notice then we got to about 50, it started to level off at 100, it kind of dropped a little, but then as we did many thousands of samples, it leveled off to the true population mean. Do you remember what that's called? Well, if you don't, okay, here it is, folks. Okay, it is the law of large numbers. If you remember, it says, draw independent observations at random from any population with finite mean mu. Decide how accurately you would like to estimate the mean. As the number of observations drawn increases, the mean x bar, okay, remember that's our sample, that mean x bar of the observed values eventually approaches the mean, the true mean, the population mean, as closely as you specified and then stays that close. All right, now if we were in class, we would be doing this. I love this activity. Every year I have so much fun with it. I think it's fun at any rate. We would simulate picking 100 randomly, selecting 100 randomly women. We'd select 100 women randomly using the calculator, okay? So what we would do is we would do the following. Okay, you can read through that, but obviously we're not going to do that because, we're distance learning at this time. But if we were in class, we would do this. So we would type in, your birth month, because I want different samples from everybody. Go through the rand, there's a rand normal. Complete the command. Okay, there's the command. And then we'd go to our one variable stats and we'd find the mean of that data. We'd write it down and then we would repeat steps 2 through 5. Since we have a small class, we probably have to repeat those steps at least 10 times, okay? Because we'd need a bunch of we want as many different samples as possible. All right, and then you'd give me the note card. Well, then what I would do, ladies and gentlemen, is I have all of these little rectangular blocks at the top, and each one of those rectangular blocks represents a sample, okay? And then down at the bottom, you see I have 64.5 in the middle, and then I count by tenths going up, and I count by tenths going down. So you would give me your results, what was the mean that you came up with, and then I would go ahead and I would go, I would take these little rectangles and I would put them in where your mean is, okay? I would do that, and it would take a little bit of time, but it's pretty cool at the results. And then if things work out like they usually do, the results are going to kind of look like that. Well, isn't that cool? Wow, okay, it turns out looking like a normal curve. Okay, so what is the approximate shape? Well, it's approximately normal, right? Where's the center? Well, the center is around 64.5, okay, which is what the population is saying, right? How does the center compare with the mean of the heights of the population of all young women? Well, It's approximately the same. Remember, we're not saying it's exactly the same, we're saying approximately. Roughly, how does the spread of the distribution x bar compared with the spread of the original distribution? Now remember, the population mean, ladies and gentlemen, is 2.5. Okay, that's 1 standard deviation, 2 standard deviations. But what would end up happening, you'll notice that, if we figured that out, the standard deviation is not quite as large. Interesting. We'll be talking about that fact, folks. All right. So that would be the little activity that we would have done in class. And again, it turns out to be, it approaches that 64.5 for the young women. And if you remember, ladies and gentlemen, our normal curve, okay, now this is based on the mean being 64.5 and the standard deviation of 2.5. Okay, if you remember your empirical rule, okay, this is, remember, 1 below to 1 above is 68% of the data. 2 below to 2 above is 95%. And 3 below to 3 above is 99.7%. Okay, we're going to be getting back to that big time with the normal curve stuff as we do the second part of chapter 5, or the second part of the book. All right, folks, so let's move on. All right, so that would have been the little activity that we did. So let's go through a few things here. All right, page 564 in your book. Parameter, okay? A parameter is a number that describes the population. In statistical practice, the value of a parameter is not known because we can't examine the entire population. Okay, that's reality, folks. Okay, it's not practical. And remember, when we talk about the population, the symbol we use is that Greek letter mu. That stands for the mean. A statistic is a number that can be computed from the sample data without making use of any unknown parameters. In practice, we often use a statistic to estimate the parameter. The sample mean is the x bar. That is the sample mean that we use. That's the symbol we use. Now remember that x bar is an estimate of the population mean. Okay, moving on. If we're talking about a population proportion, that's a lowercase p. If we're talking about a sample, it gets this nice little hat, and that's what we call it, p hat. P hat is a sample proportion. Again, this is an estimate of the population proportion, which is p. Now, when we produce samples, okay, like if we would have done this activity, okay, each time you would have gotten a different result. You might end up, some of them would have been the same result, but this result is not necessarily the same as this result, which is not necessarily the same as this result. You're going to get all these different results. That's the beauty of this, folks. So you're gathering all of these samples and you're going to spread them out. And again, if you do that, it makes that approximately normal curve. All right, so sampling variability, different samples will produce different mean values, okay? Just because I get a mean, that doesn't mean you're going to get the same mean because you're drawing a different sample. Again, I just referred back to that simulation. All right, now sample variability. Some very important things to understand. To understand why sampling variability is not fatal, we ask, what would happen if we took many samples? Here's how to answer that question. Take a large number of samples from the same population, calculate the sample mean x bar or sample proportion p hat for each sample. Make a histogram of the values of x bar or p hat, just like in our activity. Examine the distributions display in the histogram for shape, center, and spread, as well as outliers and other observations. All right, Now, sampling distributions. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Okay, we don't want to keep taking, we want to always use the same sample size. Okay, we don't want to use 10 in this one and then 20 in this one. Okay, so we have to decide how big is our sample and how many of those samples do we want to take. Remember when describing, we did this way back, I believe this is chapter 1. When describing sample distributions, you need to say things about shape, center, spread, and are there any outliers? If you forgot all about that, go back to chapter 1, chapter 2, and look at that. Page 574, unbiased statistic, unbiased estimator. A statistic used to estimate a parameter is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. The statistic is called an unbiased estimator of the parameter. All right, obviously we want unbiased information. Variability of a statistic. The variability of a statistic is described by the spread, okay, described by the spread, oops, let me make my pen there, of its sampling distribution. This spread is determined by the sampling design and the size of the sample. Larger samples give smaller spread. Ooh, more accurate that way, as long as the population is much larger than the sample. Now, the population needs to be at least 10 times as large, folks, okay? The spread of the sampling distribution is approximately the same for any population size. So, for example, if we were going to take samples from our student body, which is about 900 students, we would not want samples of 100, because 100 times 10 is 1,000. We don't have 1,000 students. Okay, so, but that would be actually doing a sample size that's too large, all right? Now, let me demonstrate, folks. This is so cool. All right, here we go. So here's this top part is a population, okay? Let's say that it's a normal population, all right? And I'm gonna take a sample, okay? I'm going to take a sample of 1, 2, 3, 4, 5, okay? And then what I did was so they each have a different mean, okay? I took the sample from this population. Here are the 5 samples, and then from those 5 samples, I found the mean. Okay, that's like picking 5 students and then finding the mean of like their height. Okay, so if I do 5 again, it'll drop it in there. 5 again, oh, different mean that time. 5 again, okay, different mean again. 5 again, and so on. So each time I'm picking a sample of 5, right? Okay, well, let's say, ladies and gentlemen, that let's say I do 10,000. Ooh, look what happened. It just automatically, look what happened. Oh, it made a normal curve. Now that's a sample size of 5. Okay, so I want you to look at how spread out that is. Now, I'm going to change the sample size. Let's say we pick 10 students instead of 5 students. Okay, again, I would go ahead and animate. Now it's picking 10 students. It's going to drop it in. 10 more students. It's going to drop it in, the mean. Okay, now here's 10,000. Oh, look at how much closer the tails have been drawn in. Bigger sample size, less spread out. Now, if I did a sample size of 20, here's 10,000. Look at how skinny that got. Okay, now, this is what's cool. The population, ladies and gentlemen, doesn't have to be normal for that to happen. I could make a population that looks like this. Look at that. Okay, that is definitely not normal, right? Definitely not normal. Watch this. And we'll talk about more of this in chapter 9.3. Okay, so if I animate, it's going to pick, this time it's picking 20, right? It's picking 20 from the population. It's going to find that mean. It's going to drop it in. Okay, if I did it again, it's going to find the mean. and it's going to drop it in as soon as it's done. All right, watch this. If I do 10,000 times, whoa, it's approximately normal. That is one of the biggest thing in AP statistics or in statistics that you're ever going to know. We'll talk about what that's called in chapter 9.3. So if you're interested, go ahead and look at chapter 9.3 ahead of time. All right, so let's keep moving. So why does the size of the population have little influence on the behavior of statistics from random samples? To see that this is plausible, okay, you need to read through this and really think about it. Pause and read through this. Okay, I'm going to read through it, and then you just have to think about it. To see that this is plausible, imagine sampling harvested corn by thrusting a scoop into a lot of corn kernels. The scoop doesn't know whether it is surrounded by a bag of corn, which is smaller, or by an entire truckload. As long as the corn is well mixed, so that the scoop selects a random sample, the variability of the result depends only on the size of the scoop. Smaller scoops, smaller samples produce wider spread. Okay, bigger scoops, less spread. So, doesn't matter if it's a bag or if it's an entire truck. It's pretty cool. The fact that the variability of sample results is controlled by the size of the sample has important consequences for sampling design. A statistic from a simple random sample of size 2,500 from the more than 300 million residents of the United States is just as precise as a simple random sample of 2,500 from the 750,000 inhabitants of San Francisco. Cool. This is good news for designers of national samples, but bad news for those who want accurate information about the citizens of San Francisco. If both use an SRS, both must use the same sample size to obtain equally trustworthy results. Okay, read through that again and think about it. Remember, we want to hit the bullseye. We want to avoid high bias. Low variability is good. Low bias, high variability, okay, we're still not very good, okay? High biased, high variability, but in the end, ideally, we want low biased and low variability. That will give us a more accurate information about the true mean. All right, ladies and gentlemen, that is it for chapter 9.1. I will see you in class soon.